let's look at an example relating to equipotential lines and just some more practice with forces and fields and equipotential. So just to point out on your equation sheet here, equipotential lines are, remember, potential or potential difference is given in voltage, right? Voltage is its units, volts are its units. And so remember when we have this, these are positive charges, it may be a little hard to see. But something with positive charge, field lines go out of positive into negative. So these lines here, this E, are the field lines. And just as we saw in here, the positive charges go in the direct field of force in the direction of the field. Negative charges feel force in the opposite direction, right? In the direction opposite the field. And equipotential surfaces are potential or surfaces where, or lines or surfaces. You may think of it in 3D as a surface where the voltage is the same everywhere. So everywhere on this green line, everywhere on this surface, the voltage is V1. If it was, say, 10 volts, it's 10 volts everywhere on this line. And similarly, here's another surface. So everywhere on this line, maybe it's all 8 volts, and everywhere here it's all 6 volts or whatever it is. And so as we are closer to charges, right, we have a higher electric field, which means we have higher potential for force. So we have a higher potential, right? Remember, potential is potential energy over charge. And so this is like how much energy it has. So higher energy, lower energy, higher potential, lower potential. And so potential is highest near the positive charges, and then it decreases as it goes out towards the negative charges or whatever, as it goes away from the positive charges. Similarly, here we can see the two plates, positive charge on the top and negative charge on the bottom, and so the field goes from positive to negative. And if we were to draw equipotential surfaces in here, they would be all little planes, like a sandwich full of different layers, right? And each layer would be a constant voltage, so each layer would be an equipotential surface inside of there, right? And so starting with a high potential at the bottom or top, and going lower and lower and lower as we get down to the bottom. All right, so we have our equation here. The potential difference is, for a uniform field like this, potential difference is the field times how far you've moved in the field, right? In fields where there are point charges, it's not a uniform field, so we have a little bit different equation. And we do have the equation for a point charge here where V is just KQ over R. Okay, so let's look at an example here. Trying to do a little bit of biology, although I don't know a whole lot about biology, but just kind of looking on the internet, try to find some good examples here. And so cells, say we have a cell in our body, and God made our body in amazing and interesting ways, and so he used electricity to get things done in our body. And so we have ions, positive and negative ions. We have voltages, so we have charges and potentials and electric fields that we can do an example with here. And so cells can be different sizes, but maybe on the order of 2 micrometers might be the size of the radius of a cell, right? But then the thickness of a cell's wall, cell membrane, might only be 2 nanometers. That should be a meter. And so this is 1,000 times different, right? So the wall is 1,000th of the radius of the thing. And so we're going to just kind of take a microscopic view and look at it and say this is the cell membrane, right? So this is the membrane here. Cell membrane. Right, and so we've got about 2 nanometers thickness across here. And just like when you look at the Earth and it looks like it's flat, right, we're going to take this part of the cell, even though the Earth is a lot bigger than this comparison, but we're going to kind of just take the cell membrane as being straight and flat, even though it's really got a little bit of a curve to it, but we're going to just assume it's pretty straight. All right, make our calculations easier. All right, so we've got some sodium ions out here, we've got some calcium ions out here, and we've got some chloride ions in here that are negative. And so another thing that I looked, just kind of trying to find some numbers to use, and so negative cells might have inside them a voltage of negative 75 millivolts. So what does that mean? It means the difference from outside to inside is negative 75. And so just like with potential energy, like when we're doing problems with gravity, we sometimes we need to know where is the reference point for potential energy. And so with these electrical problems, we can pick a spot where the potential is 0. For the point charges equation where we're doing KQ over R, we just assumed way at infinity was 0. But for this problem, let's go ahead and say this is the outside, V out, we'll call it, is 0 volts. This is the zero energy part, is the zero potential part. And so then what is V in equal to? Well, delta V is V out minus V in, V out minus V in. Is that right? No, let's do, this side needs to be lower than that side, right? So delta V is negative, so then V out minus V in, it's going to be V in minus V out is going to be negative 75 millivolts. V out, we said let's make it 0, so then that means V in needs to be the negative 75 millivolts. I should have written it maybe, well, I guess you can see it. So V in is negative 75 millivolts when V out is 0, right? So the difference inside here, final minus initial, in minus out, we'll do it that way, is even though nothing has to be moving for us to have these potentials, but we kind of think of it, and they happen at the same time, so it's not really in order. But anyway, to get our delta V to work out, we'll do it that way. So this membrane is at negative 75. This one is at 0. Draw field lines in the membrane. All right, so electric field goes from positives to negatives, goes from, when we're looking at our picture, if we forget, we can get our equation sheet out. Field lines go from high potential to low potential, right? V1 is greater than V2, so this is the highest side and this is the lower side, or from positive charge to negative charge. So our field lines are going to go this way, right? And we're assuming things are nice and straight, so they're going to be just straight uniform fields, evenly spaced, even though I think I made a mistake and made these far apart. But anyway, the E field is going like that, from positive to negative, high voltage to low voltage. All right, low voltage because it's negative, so that makes it lower than 0. So there we got our field lines inside the membrane. All right, draw the equipotential surfaces in the membrane. All right, so equipotential means same voltage levels, right? And so the voltage is 0 here, 75 here, everything's nice and straight. Equipotential lines have to be perpendicular to field lines, and so we've got a right angle here, and so they've got to look like something like this. All right, so if I theoretically did equally sized steps, we go from 0, what could we do? 0, 15, 30, 45, 60, 75, negative. So this would be like negative 15, negative 30 millivolts, negative 45, negative 60. All right, so everywhere on this line is the same potential, same energy that an ion would have, just be like being the same level above the Earth, right? If we think of gravity potential lines, it'd be layers above the Earth and how much gravity would pull you down, right? All right, so these blue ones are the equipotential lines. And we'll do some measurements and make some maps like this in lab also. All right, equipotential lines inside the membrane. Let's get back to our regular pencil. So that's A and B. How about C? Find E inside the membrane. All right, so the electric field, E, is when we have a uniform field like this. You quite often will have it between two charged plates, right? So this side has a positive charge, this side has a negative charge, so it's a charged field. We'll have a V from high to low, so V, in this case, V out minus V in. It's another delta V, but it's kind of the opposite of what we just did. Equals the field times the distance between the two levels, whatever these two levels are. That's the distance, the plane that has this one versus the distance here. So the D in this case is what I'm trying to say is going to be the 2 nanometers of thickness of the membrane if we want the field in the membrane. All right, so this is kind of negative the delta V we had up there, however we want to think about it, or just kind of take everything positive, take the magnitude of everything to get the numbers, because we've got the picture drawn here showing us which direction everything goes. All right, so the voltage difference, everything should be positive. So we got V out minus V in, so we've got 0 minus a minus 75. So this is just going to be minus or plus 75 millivolts. Well, let's just change everything to standard units so we can make sure we don't screw anything up. So what is milli? 10 to the negative 3 volts equals electric field. That's what we're looking for. I probably should have just solved this for E first before we started putting in numbers, but we can do it with this way first. And then D, like I said, is the difference in position, is the distance from wherever V out is and wherever V in is, right? Wherever the two, maybe we could say high versus low. This, to get this to be positive, we do high voltage minus low voltage kind of thing. All right, so that distance in our case is 2 nanometers. What is nano? Negative 9. All right, and so that tells us E must be 75 times 10 to the negative 3 volts divided by 2 times 10 to the negative 9 meters. So one good unit for, remember, for field is volts per meter, also newtons per coulomb, but we'll do volts per meter this time. So E is 75 E negative 3 divided by 2E negative 9. 37.5 times 10 to the positive 6 volts per meter, which is the same as saying 37.5 times 10 to the 6 newtons per coulomb. All right, that's E. Inside the membrane, right? Because of the voltage, because of the voltage difference, or because of the charges on the outsides there doing their thing. All right, so that's C. D, find the force on a sodium ion. All right, so we're thinking of now a sodium ion is at this membrane, and maybe there's some sort of a channel. You guys probably know this all better than me, but some sort of a channel for the ions to move through. And so sodium ion, we write Na plus because it is Na plus means it has one extra proton, or one more proton than electron each ion, right? So the charge Q of a sodium ion is equal to just one fundamental charge, 1 plus E, right? The charge of a proton. Why do we care about that? I'm getting a little ahead of myself because we want the force. What is the force equation? Remember from the definition of the electric field, it's kind of telling us, it's like a force field, right? We're telling us what the force is and giving a map of what the force is in all the different places. And so to find it, we just said the force is Q times E. And we're just going to do magnitudes because we know the force direction. This is positive, so the force direction is going to be in the direction of the field. So these ions are going to be pushed this way, right? So we're calculating the force. Say this is a little Na plus. What is the force that this guy feels? All right. So we can put Na. All right, so the field is the same for anybody. It's just standard field set up by the membrane, and so different charges will feel different force. In this case, the sodium charge is plus E, so 1.602 10 to the negative 19 coulombs, and E we just found was 37.5 10 to the 6th. And let's use the newtons per coulomb now, because then the coulombs cancel and we end up with force in newtons, which is what force is supposed to be, so that is nice. So the force on a sodium ion is just that 1.602 E negative 19 times 37.5 E6. Pretty much 6 E12. 6 times 10, negative 12. Yeah, negative 12 newtons. Okay. That's D. So now with E, very similar thing, the force on a calcium ion. So Ca we write plus plus, so that means the Q of a calcium ion is actually 2E positive, right? And so the force on a calcium ion is 2E little e times big E. Basically it's going to be twice the force on a sodium ion, because this one was just little e times big E, right? So it's double the force, and so it's going to be, or we can go ahead and plug everything in and calculate it, but basically we're going to get 12 times 10 to the negative 12 newtons is the force of a calcium ion, on a calcium ion in this very made up example of a possible cell that probably isn't real, but giving you an idea of how we can get some calculations done here. All right, so it would be true that the calcium ion, since it has twice the charge, would feel twice the force, right, in the same field set up in the membrane of our cell. All right, I think we'll go ahead and stop there.